Hello everyone and welcome to your historical geology lecture. This is kind of a weird one. So the last one we had was number 12. When I'm keeping the numbering the same even though we're kind of skipping some material. So we're going to skip lecture number 13. That was because we lost a week, you might remember, with the winter storm. And we're going to move on to lecture 14. And actually what I did is I just kind of combined lectures 14 and 15 and cut some material. So it's going to be kind of a longer lecture because it is actually two lectures compressed and consolidated, but I cut stuff, of course, so it'll fit. But we're going to be talking about basically the very beginnings of Earth now. So we got done with geologic time and radiometric dating. We learned about all the techniques that we use to explore the history of Earth, the scientific techniques. But there's now the task of going through and actually learning the history and what actually transpired and happened through the ages, right? So we're going to start at the beginning, right? And in the beginning, we had a very definite beginning to the universe. It's not infinite, and there's not infinite stretches of time. There are vast stretches of time, but not infinite. There was a single point in which all the universe came into existence. That's the Big Bang. And we're going to learn about that, where our universe came from very briefly. Learn where our solar system came from very briefly. And then we're going to move on to the early first eon of Earth. That's called the Hadean. So we're talking about origins of all the universe, basically the origins of the universe, and the Hadean eon. Okay, so let's get started because we have a lot of material to cover, right? So where did the solar system come from? We have the sun, and we're one of the planets going around the sun in the solar system. We have 7 other planets and many dwarf planets, including Pluto. So where did that all come from? Well, its origins, the origins of the universe from a scientific standpoint were pretty mysterious for a long time. Up until the middle of last century, with kind of characters like Edwin Hubble, and Einstein, we didn't really know very much about really where the universe came from a scientific perspective, right? So it was really kind of eye-opening what Hubble, Einstein, and other scientists here too, Lemaitre, who's not so famous, what they discovered during the last century. There were a lot of theories about where the universe came from. Some people thought at that time that a lot of scientists thought that the universe was just infinite, that it didn't have a beginning and it doesn't have an end. And it's just a brute fact of existence. But rather we found something rather shocking last century. We found that there was a single moment in which the universe came into existence, and it seems that all matter, time, and space originated from a single point. Okay, that point is called the singularity. Okay, so the singularity is right here. So time began 13.7 billion years ago. It originated at a very small point in space called the singularity. And that theory that all time, space, and matter originated from that single point is called the Big Bang. It started with a massive explosion, massive expansion. The Big Bang was actually originally theorized by a Catholic priest in 1927 who was also a very skilled mathematician and a very skilled astronomer and astrophysicist named Father George Lemaitre. He's a Belgian priest and scientist, and actually was able to solve, kind of impressively, he was able to solve some of what was called matrix calculus operations that Einstein himself was having trouble solving. So he was able to solve these matrix calculus problems that allowed him to kind of go back to the original point at which, salt. I'll get to it eventually, but you'll see what I mean. But all of the galaxies in the universe are moving away from a single point, and you needed the matrix calculus to figure that out from the current directions of the galaxy motions. So, anyway, that's kind of the Big Bang in a nutshell. So, at this very single moment, that's when time, space, and all matter seem to come into existence. So, why do we think the universe began with the Big Bang? Okay, so what observations led us to conclude that? So, a lot of this was based on the astronomical observations of Hubble, Edwin Hubble, an American scientist, and he noticed something we call redshifts. Perhaps you've heard this term before, redshifts. What a redshift is when you look at a faraway star, the further that the star is, the light coming from the star is a little bit redder than it should be. So stars, depending on their size, are going to have different temperatures, okay? And you can correlate the size of the star with its temperature, and therefore the color of light that's coming from it. Hotter stars burn blue. Cooler stars burn kind of yellow, white. Our star is sort of a medium star. It burns yellow, kind of a yellowish white, right? Stars that are cooler are more red, okay? So what Hubble noticed is that stars that should be more bluish light are a little bit more red than they should be. Everything is a little bit more red than it should be as the distance from the star increases. So as we look at progressively further and further away stars, the light coming from them seems a little bit more red than it should be. That was a very interesting, very strange observation. Why should that be? Well, Edwin Hubble realized that this is actually a Doppler effect. So as a star moves away from you, the frequency of light, or I should say the wavelength of light, is sort of stretched out, okay? As it moves toward you, the light is squished together. The light waves are squished together, and that makes a smaller wavelength, a higher frequency light that appears more blue, okay? This is related to electromagnetic spectrum. So you might remember seeing the electromagnetic spectrum before. The longer a wavelength is, so wavelength of light, so light is a wave, right? The longer the wavelength, the more red it is. Okay, so look at the wavelength of red light and compare it to this purple light. Okay, you see how this is a very short wavelength, this is a very long wavelength. So basically, the way you can think of this is that the light waves are getting stretched out when a star is moving away from us. And so the star's light appears more red than it should be because it's moving away from us. Okay, so does that make sense? Hopefully, I can't hear your answer, but hopefully that makes sense. All right, so Doppler effect, you all know Doppler effect. It's like if you go, let's see if this pops up here. Or actually, I don't think that's going to work. Let me see. Yeah, it doesn't work on my Firefox. Let me go here. Try it here. So you all know Doppler effect. It's the same as when you hear, have you ever heard like a car coming towards you honking its horn? And at first the horn sounds like kind of like very high pitched, and then it passes you and it starts to sound low pitched. So we're going to show you. This guy's going to blow a trumpet in a car, and you're going to see how it sounds when he's in the car versus an outside bystander. Hopefully this will pick up on the... Hoping you guys can all hear this coming from my screen. Okay, so that you can hear he just played one single note, right? But look how it sounds when when you hear him drive past. So you might notice that as he comes towards us, hopefully you're able to hear it. Maybe I should turn up the volume a little bit here so I don't have it all full volume. So you can listen to the tone and then listen to it when he passes and comes towards us and passes us. Okay, so the moral of the story is, as you move away from the source of the sound or the source of the light, it's going to change the frequency. Oh, whoops, it's going. It's still going. Oh my gosh. There we go. So that's basically what's happening with redshift, okay? I could show you this other one here, but hopefully you get the idea. So as light moves from far-off stars, as the stars move away from us, the light they emit appears to be at a lower frequency, more red than it actually is. Okay, so what does that all mean? What does redshifts all mean? It means that stars that are further away are moving faster. It means that stars that are moving away are moving faster. Stars that are closer to us are moving more slowly. And what that means is that the stars that are moving faster, the reason that they're further away is because they're moving faster. They have more time. In the same time, they have moved further out into the reaches of the universe. So what you can do is extrapolate backwards and you realize that all of the stars basically started off from the same point. So for example, if you imagined, here's point 0, okay? And we're 10 miles away and we're moving 10 miles an hour. Okay? And then there's another star over here and it's 20 miles away. Whoops. It's 20 miles away. And it's moving faster. It's going 20 miles per hour. You would realize that if we extrapolate back in time, 1 hour ago we would have been at the same point. We would originate at the same point. So basically, this is what I'm trying to tell you all, is that if you extrapolate backwards and go back, kind of rewind the tape, you realize that we would all be starting off at the same point, all of the stars and all of the galaxies. Okay, so that's what we learned from redshifts. So the bottom line is, it seems that from redshifts that the universe has expanded from a single point in both space and time. Okay, so it's pretty amazing. I mean, you can imagine what an amazing discovery that was, and there was a lot of pushback as well against Father Lemaitre, his theory, but it was eventually accepted by Einstein and accepted by big names in astrophysics, and that really, we've come to accept it now as truth. So most of the matter generated from the Big Bang was hydrogen. Okay, so in the first microseconds, I mean not even a second, microseconds of the Big Bang, we had hydrogen. Okay, so hydrogen and some maybe minor amounts of helium. So hydrogen, remember, is element number 1. Helium is number 2. Lithium is number 3. Okay, so we started off with just hydrogen, helium, and lithium. That's what the Big Bang created. Okay, but mostly hydrogen. So, we have other elements, right? We have carbon, we have oxygen, we have iron, we have 92 naturally occurring elements. So where did all that come from? So in the first microseconds, 10 to the negative 6 seconds after the Big Bang started, after time began, we had protons. After 100 seconds, we had deuterium, helium, and lithium. Deuterium is a type of hydrogen. After 100 million years, we had the first stars form. And it wasn't for another 4 billion years that star formation really peaked. And it wasn't for, another 9 billion years that our star came into existence. So actually, our star is rather a latecomer, really. So how did our sun form? How did our solar system form? That's kind of a very brief history of the universe. But how did our sun form? That's a good question, right? I'm going to pause this for 1 second here. Okay, I'm back. Sorry, I had to take my dinner out of the oven. Turned out pretty well, by the way. Sorry. So, anyway, how did our solar system actually form? So we went over already, where the universe came from, basically. How about our sun? So the way our sun formed are from these clouds of hydrogen and other elements as well, but mostly hydrogen. 99.9% hydrogen, because what was created in the Big Bang was basically a lot of hydrogen, right? It was probably 99% hydrogen. Most of the universe, the mass in the universe, by far, most of the mass of the universe is hydrogen. Okay, so it was mostly hydrogen, and it got so large, this cloud of dust, cloud of gas, that eventually it started to collapse. Okay, it's gravitational collapse. So the density of the gas got high enough that the gravitation, right, mass attracts mass. So the mass of gas in the cloud became heavy enough that it started to attract more gas and eventually to collapse and condense and attract into one single object, right, which became eventually the sun. So it began to collapse. As it collapsed, it started to also to rotate. Okay, so as matter collapsed into the solar system, it started to rotate out, and as it rotates, imagine like a potter's wheel or some clay, on a potter's wheel spinning very fast. What happens? It starts to be pulled out by centrifugal force. So this cloud of gas began to pull out and extend and flatten into a disk. Okay, so that's how all nebula, eventually become a solar system of some kind. Okay, so that's just kind of what we call the nebular theory of this creation of the sun. So as more and more mass accretes together, accretes means comes together. Okay, the gravitational pull becomes stronger and stronger and stronger. A proto-sun is born, because basically what happens is, remember, a mass attracts mass. So let's say you start off with a little ball of hydrogen. Well, when it starts off with a little ball of hydrogen, the gravitational force is maybe small, like that. But then it's able to pull more hydrogen in. And when it pulls more hydrogen in, gets bigger, the gravitational force gets even bigger. And it's able to swallow up even more hydrogen. And as it does that, it gets bigger, and its gravitational force becomes even larger. Okay? So there's what's called, a snowball effect, right? So eventually, these objects become so large, they swallow up all the hydrogen. They start to rotate, and they flatten out into a disk shape. Okay, so that's how the sun is born, and that is how the planets eventually are born. This disk of rotating material eventually condenses and accretes into the planets. Now, where does the energy of the sun come from? So I just mentioned hydrogen. So what's going on in the sun to actually make the energy? What is happening is that there's a process called nucleosynthesis. Okay, nucleosynthesis. So nucleosynthesis involves a nuclear fusion. Okay, nuclear fusion. So hydrogen atoms come together. If you take 4 hydrogen atoms, you can combine them together to make helium-4. That is a helium, right? Helium-4 is equal to having, 2 protons and 2 neutrons in the nucleus. Okay, so you can combine those hydrogen together, and they will release a tremendous amount of energy. That releases a tremendous amount of energy, and it makes a helium-4 atom, and it releases a particle called a neutrino. Okay, you don't need to know that, but you do need to know that hydrogen comes together to form helium, and it releases a tremendous amount of energy. That is called hydrogen burning, and another term for it is nucleosynthesis. Okay, so as the protosun gets bigger and bigger, pressure increases until the nuclear fusion begins. Okay, so hydrogen atoms, basically because of the pressure in the center of the protosun, gets larger and larger and larger as the object gains mass. The hydrogen gets squeezed together until it's squeezed so tightly together that they bind to form helium. Okay, so the first nuclear fusion reaction to occur in a star is hydrogen burning, which forms helium. That process of building a new element is called nucleosynthesis. So any time that you use nuclear fusion to make a new element out of a different element, that's called nucleosynthesis. Okay, so that is how all the different elements of our solar system were found. Okay, at least a lot of them. They are found from nucleosynthesis. You're building larger and larger atoms and more complex sorts of atoms from hydrogen, ultimately. Okay, so that explains where hydrogen and helium come from, but what about other elements? Like, where does carbon come from? Where does oxygen come from? Where does iron come from, right? So there are 92 naturally occurring elements, right? So the naturally occurring elements there are shown in green, okay? So where do those all come from? So as the sun starts to get hotter and starts to burn off its hydrogen, other processes start to occur. So another process that starts to occur is helium burning. So usually what happens with a star is you have a core in which there's hydrogen burning going on. And then in a outer shell, there's helium burning going on. So the helium now is combining together. You have 3 helium-4s, and that makes a carbon-12. Okay? So that is called helium burning, and that's how carbon is created. There are a lot of different nucleosynthesis reactions that will create all the different elements of the periodic table up to iron. Okay? So for example, carbon-12 can burn, and you have carbon burning. Carbon-12 can react with carbon-12 in a nuclear reaction, create oxygen. It can create neon, it can create sodium, it can create magnesium under different conditions as well. Okay, so the production of carbon makes a gateway for a lot of different other elements to be created in these kind of subsequent shells. So after the helium burning shell, then there's going to be on the outside a carbon burning shell. Okay, so you're going to be burning carbon in there, and then even subsequently heavier and heavier elements are going to be created in other shells as you move away from the core where helium burning is taking place. So carbon can combine in fusion reactions to form other elements such as oxygen, neon, sodium, magnesium, etc., etc. So it goes like this. You can see, oh, I'm sorry, I had it backwards. Sorry. Hydrogen burning is going on the outside with subsequently heavier elements being burned towards the core. Sorry, I got it backwards. So anyway, these are all different. I asked you on your lecture assignment, I think, if I didn't nix the question, I might have asked you for a some kind of reaction, some kind of nucleosynthesis reaction. You can write down any one of these: neon burning, oxygen burning, carbon burning, silicon burning. You should definitely know, though, that hydrogen burning is the main nuclear reaction that's taking place in the sun to make all of its energy. Okay. So the reason, by the way, that the sun doesn't just collapse and become a black hole is because of the thermal pressure pushing out from all these burning processes. Okay. So eventually when the fuel gets used up, the sun is going to collapse and it's going to become a black hole. So you might notice that as all these different layers of elements are created, the last element that can be created is iron, and nothing heavier than iron can be created in the center of a star. Okay, so nucleosynthesis, normal nucleosynthesis, ends with iron. That's the heaviest element that can be created. Iron is element number 26, so you can't get any heavier than iron. So these elements all here, these are all elements that could be created in stars by nucleosynthesis, all the way from hydrogen to, titanium, vanadium, chromium, manganese, and iron, all the way through to carbon, nitrogen, oxygen. All these things can get created in the nucleus of a star, but nothing heavier than iron. Okay? Well, that's kind of interesting, because you know that we have things on Earth that are heavier than iron. We have mercury, we have gold, we have zinc, we have copper, we have nickel, right? We have tantalum, barium, and radium, and all this stuff. Where did all that come from, right? Because you can't create it by nucleosynthesis. So the process of nucleosynthesis in a star can continue only up to iron. So why is that? It's because every time that you react, this is showing energy release as you move up in the mass number. Okay, remember we learned about mass numbers in the last lecture. So as we go from hydrogen to helium, there's a huge energy release. As we go to helium to other things, there's big energy releases, up to iron, right? And iron has the most energy. And from there, it takes energy to make subsequently heavier elements, okay? So iron, another way of looking at it, this is the mass per nuclear particle. Iron is here at this inflection point, okay? So it's basically the maximum energy that you can have, okay? Binding the nucleus together, okay? After that, it takes energy to create elements, okay? So that means that everything heavier than iron, it's going to take energy to create those elements. Where does that energy come from? It's not coming from nucleosynthesis. The answer is supernovas, okay? So everything heavier than iron originates in a supernova. During a supernova, that's what happens when there is a star, an old star has burned out, it's used all of its fuel, it has turned into an iron ball, and it's died, it's gravitationally collapsed, and the mass is so large that it completely collapses, turns into a black hole, and eventually the mass it collapses to the point that there's an explosion, and that's a supernova. Okay, a supernova is an exploding star, and that massive release of energy is enough to create elements heavier than iron. So anything heavier than iron had to be created in a supernova. So this is interesting because it shows that our solar system could not have been the first solar system in this part of our galaxy. We came kind of riding on the britches, riding on the coattails of a supernova. And it's quite possible that the nearby supernova is what caused our particular solar nebula to collapse gravitationally and become condensed into our sun that we have today. Okay? So we are what's called a second generation star. So the stage A of our solar system formation was the supernova of a pre-existing star. Okay, because our solar system is filled with elements heavier than iron, meaning elements with higher atomic numbers than iron, we know that there must have been a supernova prior to the formation of our solar system. Elements heavier than iron can only be created in a supernova. So stage B is that hydrogen, dust, heavy elements, compounds form slowly, and they start to rotate around in its nebular cloud. The early solar nebula gravitationally collapses, the mass contracts, and it forms a protostar that is not yet ignited. So as the sun grows larger and larger and larger, pressure in the interior increases, pushing the hydrogen closer together. When they get squeezed so much, they initiate fusion, which releases a lot of energy, and in turn provides energy to ignite other hydrogen atoms and cause them to react as well to form helium. So it ends up starting a chain reaction that creates the burning sun as we have it today, right? Burning hydrogen. So hydrogen fusion is the source of our solar energy. Okay, by and large, it's the major source of our solar energy. Sorry, my daughter walked in through the door. Now it's locked. Okay, so stage C. The protosun swallows up 98.6 of all the mass in the nebula. Okay. And that intense pressure at the center of the protosun initiates nuclear fusion. And we start to get disk rotation. We start to have the nebula flattening out. And that's what eventually leads to the planets accreting and condensing. Okay, so as the temperature of the early solar nebula, it was enough to vaporize. It was extremely hot. Okay, so the temperature of the early solar nebula is very, very hot. So material with a higher melting point condensed near the sun, and material with a lower melting point condensed further out. So that's why close to the sun, you get the terrestrial planets. You know, Mercury, Venus, Earth, and Mars, which are made of rock and metal. If you get out further away, the temperature goes down, and you get the icy planets, right? So Saturn and Jupiter and Uranus and Neptune. Okay, so that's the nebular hypothesis. Okay, that just shows the evolution of the solar system, starting with a cloud of dust and gas. Okay. So how did the planets form? They form from accretion. Okay, it's an extremely important process. So meteorites, asteroids, space objects, which are combinations. By the way, they're combinations of dust, rock, and metal. Okay, so it's a mishmash of rock and metal. If you get a meteorite, if you ever lucky enough to find a stony meteorite, it is a mishmash of rock and metal, like our Earth is. Okay, so the rock and the metal were being sucked into, it's the same process as what was going on with the sun, right? You start off with a small object, and let's say you have a lot of little things out here. That small object gravitationally attracts, and it sucks up all of this material. Okay, so then you move to the next thing. It gets bigger, right? And then when it gets bigger, it has a higher gravitational attraction, and it's able to suck up things that are even further away. Okay, so it sucks those things up. It gets even bigger, right? So that's what's going on. It's a snowball effect. And as the planet grows, its mass grows, it gets larger. It's able to suck up further and further and further material that's further and further and further away. And it becomes larger and larger and larger. Okay, so as protoplanets grow larger, their gravitational force fields increase and they attract more material. Okay, so that material consists of meteorites, asteroids, and comets. And as the as the planet accretes together, it heats up from the high kinetic energy of the moving bodies. So every time that a meteorite strikes Earth, it releases tremendous energy, right? You can see the tremendous energy being released. And that's enough to heat up the Earth. So, by the way, it might surprise you. I find this amazing, but a lot of Earth's heat that's still trapped deep within the core, deep within the mantle, that is still just residual heat left over from the accretion process. Okay, we're still 4.5 billion years later, just cooling off from that bombardment of meteorites. Okay. So asteroids release a lot of energy. This energy heats up the early Earth. And it's hot inside the Earth, right? So a lot of that heat, it's just leftover residual energy from the accretion of our planet. The other source of energy is radioactive decay of elements such as potassium, especially potassium, and uranium. That also adds some heat to the interior of our Earth. So it didn't take very long after the formation of the sun for the planets to form. So this is the present time. If you think of this bar as timeline of Earth, this is the present. This is the formation of the sun. It was only 10 million years later that the planets formed. So it happened very fast. Okay, so the planets and the sun formed very quickly. And the moon, along with it, the moon formed very quickly. So we're going to move on to, now we have planet Earth, and we're going to, planet Earth has accreted together, and let's talk about this first time period. So this time period is called the Hadean. Hadean is a reference to Hades, which is, you might know from Greek mythology. Hades is the god of the, he's not the god of the underworld, but Hades is the underworld, the name for the underworld. So it's like hellish, right? can't remember. Gosh, the name of it is escaping me. The name of man, I don't know why I can't remember it. Zeus, Poseidon. Was his name Hades? I can't remember. I'm totally blanking on the name of the god of the underworld in Greek mythology. It's okay, it doesn't matter. But Hades is the place, right? It's basically like hell. So this was a hellish landscape. So take a look at the picture here, and let's just I'm going to kind of use this picture to guide our discussion of the Hadean. Okay, so take a look at what do you see here. So there's some interesting things. We're going to go through that picture and focus on some of the interesting things we see. So the Hadean is the first eon, first of the 4 eons. It started, right, 4.56 billion years ago with the creation of Earth, and it lasts all the way to 4 billion years ago. Okay? So it only goes about 560 million years, right? So there's the Hadean. It's about 13% of Earth's history. We classify it as the Hadean. Okay, we cut off the Hadean at 4 billion because that's the kind of the earliest rocks that we have. Okay, so these are some of the big events that occurred during the Hadean. We'll talk about all these. Some of these we've already talked about. So the Earth condenses. Okay, water first starts to come up onto the surface. We don't necessarily have oceans yet, but we have some surface water and some water in the atmosphere. We get the formation of our atmosphere. I don't even have that here, but we have an atmosphere at that time. We get the formation of the moon. We get the accretion of the core. So it's called core differentiation. We start to have a magnetic field. And the only thing I don't talk about here is I don't talk about the late bombardment. There are some geochemists that believe, basically to make the chemistry of Earth work out, that there must have been a later bombardment of meteorites after the initial accretion of Earth. So I don't want to get into all that. It's kind of deep geochemistry that you don't need to know at this point. But just kind of so you know that it's a thing. I introduce it here. So we already talked about Earth coalescing together. So we have Earth's formation and accretion. We have something called differentiation, in which the crust starts to form. The core starts to differentiate. So Earth becomes different, right? It starts off as homogeneous material of a homogeneous mixture of metal and rock, but it starts to differentiate. So it becomes different. So we have, right now, you know that we have a metallic core and we have a rocky mantle. Okay, so it wasn't always that way. Everything was mixed together. During the Hadean, we have differentiation. Okay, we have the moon forming. We have melting, and we have outgassing. Outgassing means that all the gases that are trapped within the Earth, all of the liquid water, is going to start to be released onto the surface. So we do not have any rocks from the Hadean. We do not have any minerals. Well, we might have a mineral surviving from the Hadean. Oh yeah, Hades. Hades is his name, isn't it? Gosh, I can't remember. This is killing me. I'm going to look this up as soon as I'm done with this. I'm going to remember. I think his name is Hades. But the place is also called Hades. Whatever. So the Hadean Eon, you have planetary formation. Okay, here's just, again, a quick kind of timeline of what happened. So 4.57 billion years ago. Okay, so Earth formed maybe 4.55 billion years ago. Only 4.57 billion years ago, so just 10 million years before, we had the supernova and the nebular disk formation. So the sun, the solar system, they form in only 10 million years. We have ignition of the sun just 3 million years later. We have protoplanets 10 million years after that. Core differentiation is basically complete after 30 million years. And we have moon formation after 40 million years, okay? And the first crust and the first possible plate tectonics are maybe starting to happen during this time as well. And there's lots of melting, okay? There's lots of melt. There are some people, we're not sure. There are some people who think that at this time Earth was totally molten, and that's possible. There are other people who say no, it could not have been totally molten. I don't get into all the details of those arguments in this class, but it's something you should be aware of, okay? So our oldest rock, again, is 4 billion years old. That's when we make the cutoff of the Hadean. Okay, it starts with the oldest rock, the Acosta gneiss of Canada. You should know the Acosta gneiss. I could very well ask that on the test. Hey, what's the oldest rock? The answer is Acosta gneiss. And you should know how old it is, too. I could ask you how old, or I could ask you on the test, how old's the Acosta gneiss? You should know it's 4 billion years old. Okay, for GA. We do have zircons, which are very, very tough little minerals that are found in Western Australia that have been dated to 4.4 billion years, but this is contentious, okay? So, some people doubt it. The atmosphere at this time, we had no oxygen, okay? We had no oxygen. The advent of oxygen was a very big deal on Earth, and we did not start off with oxygen, okay? Our atmosphere was mostly water, methane, ammonia, and H3. CH4 is methane, H2O is water, H2, which is hydrogen, N2, which is nitrogen, and CO2, which is carbon dioxide. So we have these gases. We have CO2, N2, nitrogen 2, N2. That's right now. That's 78% of our atmosphere, right? So we have a lot of these gases still. We still have a lot of water in our atmosphere, right? Our atmosphere is like maybe 2% water. We still have methane in our atmosphere, right? So a lot of these things are around still, okay? But there was no oxygen, and that's a big deal. Okay, so there's Hades. Let's take a look at some of these different characteristics or aspects of this drawing, okay? So what are some things you notice in this picture? Okay, so first notice these asteroid collisions, okay? So obviously during the Hadean, you still have asteroid collisions very frequently, okay? So this is how Earth accreted together. So it makes sense that it's still growing in size, its gravitational field's becoming stronger, it's sucking more and more material into its gravitational zone. So during the Hadean, Earth was clearing its orbital zone and sucking all the nearby material into itself, okay? So asteroid collisions, released a lot of energy. There were also not only asteroid collisions, but there were probably collisions with even protoplanets. So this is what's being shown in this picture right here. You probably had small planets like dwarf planets running into Earth as well. Certainly happened on other planets. That's why, for example, Venus, might interest you to know that Venus rotates backwards. So it spins in the opposite direction of the other planets, okay? We think the reason that it does that is due to a major collision, okay? So, a planet-sized collision. So that accretionary energy was probably sufficient to melt almost the whole Earth. There was a lot of energy being released, very hellish, melting, volcanic landscape, right? So take a look at this celestial object. What's that supposed to be? What is this giant thing that's close to us? So that is actually the moon. So some things you might notice. Why is the moon so big? Why is it molten? And did we really have a moon back then? So I'm going to give you the answers to all those questions. So why does it look so big? Well, it might interest you to know that the moon has been slowly moving away from Earth over geologic time. So when we started off, we estimate that the moon was maybe only 15,000 miles away from Earth. Very, very close. It is currently 240,000 miles away from Earth on average. Okay, so 15,000 miles is very, very close. Okay, and the reason that it gets a little bit further away every year is because actually the tidal frictions that it slows down its orbit. So the friction that it feels from constantly having to move the tides, move the ocean water, and a little bit of the rocky material of the planet, that actually is enough to kind of slow down and suck up some of its gravitational energy, and so thus it actually loses, you can almost think of it as almost kind of losing its grip every day on Earth, and so it slips a little bit further and further and further away. Okay. Amazingly, just amazing technology, the average distance to the moon is measured very accurately with a laser. We actually have a laser that shines from Earth onto the surface of the moon where the astronauts installed a mirror. Okay, they installed a mirror. It reflects the laser back, and we measure the time that it took the laser light to come back. And that's how we get an extremely, extremely precise distance from here to the moon. Okay. So every year the moon gets about 3.78 centimeters further away from Earth. So if you do the math and go backwards, you'll notice that the moon would have been 133,000 miles away instead of 240,000. Okay. So it was very close at that time. So another question: when did the moon form? Okay, so the moon formed very early on in Earth's history, and the way that we know it is because we have moon rocks, and we can radiometrically date those moon rocks, and we see that they are very close in age to the age of the Earth. Okay, so the moon rocks brought back from the Apollo missions appear to be about 4.53 billion years old, which is only 30 million years older than the age of the Earth. Okay. Now, how did the moon form? That is a question we do not know for sure. There are a lot of hypotheses, and the most popular hypothesis is a hypothesis called the giant impact theory. I shouldn't call it a theory, it's the giant impact hypothesis. You should remember that even though a hypothesis is favored by a lot of scientists, that doesn't mean that it's true, right? So a popular hypothesis, even if all of the experts subscribe to that hypothesis, that doesn't mean that's still just a hypothesis. So we don't have very much evidence backing this up, and the evidence is very confused and contradictory, but it is the most popular hypothesis at this time. So a popular hypothesis is the giant impact hypothesis. So according to that hypothesis, about 4.53 billion years ago, a Mars-sized planet collided with Earth. It ejected a tremendous amount of material into space, and some of the ejected material coalesced to form the moon. So basically, we can simulate this, and it kind of looks like that. Okay, and somewhere in there, oh, I guess that's the moon right there. Oh, I can't, it's not going to go around with it, but anyway, that's how the models have everything play out. I would love to spend a whole lecture just going over this hypothesis and what the problem with it is and what its strengths are and what its weaknesses are. It's not a perfect hypothesis. It still has a lot of things that need to be explained, and a lot of things that don't make sense. But anyway, it is the most popular hypothesis. So the moon has been so some of the reasons that people think this is true is because the moon has a very small metal core. If the moon had accreted like the Earth from meteorites and asteroids, it would have had more iron and it would have had a larger core. So that's why people maybe think that an asteroid came and kind of scraped off some of the material of Earth. The moon is also composed of very high melting point or refractory material, as if it cooled from a very, very high temperature. Okay, so some reasons, though, that this does not make sense. According to all the models, the moon formed from a giant impact. If it formed from a giant impact, it should be mostly made of the impactor, not of Earth. So the whole reason we believe this hypothesis is because we were thinking maybe it scraped some of the where's the metal? We're thinking maybe it scraped some of the mantle off of Earth, and that's how the moon formed. But we find that really all the models say that the impactor should be the thing that makes up the moon, not Earth. So the moon is also isotopically very similar to the Earth. So it does seem that in terms of isotopes and in terms of chemistry, the moon is a lot like the Earth. But according to the giant impact hypothesis models that simulate it, it's actually would be made out of the impactor, not out of Earth. So, like I said, there's kind of back and forth about this, but I think the bottom line, nobody really knows for sure where the moon came from. So, remember, a hypothesis, no matter how popular among experts, still just a hypothesis. I always like to say things like this because, oh my gosh, scientists can have not the most humble people in the world. Let me just say it that way. So I like to remind people that a hypothesis, even if it's very popular, it's still just a hypothesis. So let's take a look at this picture again, see if there's anything else that's sort of interesting about it. So we talked about the moon. Notice it's molten, right? And the reason that we show it molten is because the giant impact hypothesis, we think that the Earth would have been, or the moon would have been totally molten after forming from the giant impact. And it does indeed seem to show that the whole surface, when we looked at the surface of the moon from our lunar explorations, it seems like, yeah, this was a pool of magma. This was totally molten at one time. Okay, so this is probably accurate, showing the moon very close as a ball of magma. You probably notice widespread volcanism. Okay, that's because, again, the high temperature of the interior of the Earth caused a lot of volcanism. Okay, inside of Earth was much hotter than it is right now. So this could have been Earth 4.5 billion years ago, right? These just almost entirely molten planet. Lots of volcanoes, lots of lava erupting onto the surface. Okay, so could be entirely molten at this point. Now, during this time, the Earth also differentiated. That means that the core, the metal, separated from the rocky material. Okay, so as the Earth was mostly molten at this time, possibly entirely molten, it was able to kind of separate, just like oil and vinegar. If you mix up oil and vinegar for salad dressing, it's going to be kind of like homogeneous at first, but if you give it time in the liquid state, it will separate. Now, if you were to put that oil and vinegar into the freezer, it might not separate out, right? It would get frozen and would get stuck. But once it melts and it's totally molten, totally liquid, it's able to separate and condense, right? So Earth is 2/3 rock, it's 1/3 iron, okay? So where did all that iron metal come from? Well, it comes from meteorites. So meteorites, to this day, meteorites that fall to Earth are magnetic. They contain a high amount of metal. So all of those meteorites that impacted Earth 4.5 billion years ago still have that metal, and that's where our metallic core comes from. One thing that's pretty cool is, there are stony meteorites like this one, and there are metallic meteorites like this one. It might interest you to know that metallic meteorites that you find are actually the cores of planets that have exploded. No joke. Serious about that. So anytime you find an iron meteorite, there's a lot of jewelry made of iron meteorite, just know that you're holding a piece of an exploded planet. It's kind of cool thought. So meteorites have a composition, so not iron meteorites, but stony meteorites, which represent kind of primitive material of the early solar nebula. So if you want to know what the early solar nebula is, get a stony meteorite. That's going to tell you. So stony meteorites have an elemental composition that's nearly identical to that of Earth. It's kind of cool. So basically, if you were to mix up the Earth, put it in a big blender and mix it all up, and you mix up a whole bunch of stony meteorites, you wouldn't be able to tell the difference between them chemically. So stony meteorites have a lot of metal. That's why they're magnetic, and that's why we have a core. Okay, so the dense metallic material and the lighter rocky material started, at first they were kind of in a mishmash, but eventually that heavy iron material sunk into the center of the Earth, and the lighter stuff moved up and became the crust. Okay, so you formed the mantle and the core. Okay, that's how it happened. So core formation probably complete within 30 million years of Earth's accretion. Happened very fast. And we also have evidence that Earth started to have a magnetic field in the Hadean. So the outer core is liquid. Remember that the outer core, we didn't even have an inner core at that part. Probably it was all liquid iron at that point. The core was totally liquid iron. And that liquid iron was sloshing around. It was circulating with the rotating Earth at that time. Earth was definitely rotating. And it is composed of that liquid iron, circulating. So that means that we're going to have a magnetic field. So there probably was a magnetic field. There probably was, aurora borealis at that time, just like we have today. So remember that Earth's magnetic field is produced by convection and circulation of the iron, liquid iron in the outer core. And so yeah, that was a thing back then too. So what else do we see in this picture? Let's go back to our picture here. Take a look at other aspects of Earth that might be interesting. So we see these clouds. So, good question is, was there an atmosphere back then? So there's actually a lot of gas, water, and other fluids trapped in the Earth, right? And you still, to this day, if you go to a volcano, you see a lot of gas being released, sulfur. You can see the elemental yellow sulfur being belched out of this volcano, condensing onto the Earth, right? There's sulfur, there's oxygen, there's a lot of, mostly it's actually water and carbon dioxide. So yeah, all this stuff you can imagine in the Hadean, there's all these millions of volcanoes just belching out all of these gases that are from the interior of the cooling Earth. So the atmosphere and oceans were probably built up little by volcanic outgassing. So just all of the water being poured out of these volcanic events eventually became our atmosphere, and eventually it formed clouds, rainfall, and it filled up the basins. I mean, what an amazing, wouldn't it be so amazing to just be able to watch these processes happen, and fast forward like time-lapse cameras, and just watch all of the water being belched out of these volcanoes, forming the clouds, forming the atmosphere, and eventually the rain. Imagine that. Wouldn't that be amazing? Think of the first rain to fall to the Earth, to cool the Earth, and start to fill up the basins with water. And you have the first oceans, and you have the first separation of the land and the continents and the oceans. So it's really, really amazing to think about, the creation of Earth and all that. So another hypothesis that it used to be kind of more popular, but I think it's slowly starting to lose traction as more isotopic evidence from comets starts rolling in. We have more chemical data rolling in from comets, from rovers and spacecraft that we have landed on the surface of comets. But one hypothesis that's still out there, although it's diminishing, is that comets brought at least some of Earth's water. So comets are composed of ice, and not just liquid water, or not just solid, icy water, but also other stuff. But that collisions with comets maybe brought some of this as well. So that's another hypothesis. So the Hadean atmosphere was probably hydrogen, helium, ammonia, methane, nitrogen, carbon dioxide, lots of water, right? So notice something's missing though, right? No oxygen. So you could see these gases escaping from the inside of Earth by volcanic outgassing. So the volcanoes are releasing water into the atmosphere. So why is there no oxygen? That's a good question, right? We have a lot of things, we don't have oxygen. Okay. Here's, again, this picture, you see the asteroids coming in, by the way. You see the moon up close, so just kind of reminding you of those things, what was going on there. So anyway, we have volcanoes. They're releasing carbon dioxide, they're releasing water, but they're not releasing really much oxygen. Right now we have 21% oxygen in the atmosphere. What happened? Where's that oxygen? Why don't we have oxygen at this time? So also remember, we have no rocks preserved from the Hadean. Okay, the oldest rocks, the Acosta gneiss, 4 billion years old. Okay, so that came at the end of the Hadean. So it is kind of cool though, because this is a metamorphic rock. It's a gneiss. Remember that metamorphic rocks have a protolith that must have predated the Acosta gneiss. So it appears that the Acosta gneiss, the protolith of the Acosta gneiss, was a granite. So a granite is a continental rock. So it seems that at that time there probably were continents. Okay, so probably there was continental crust. And remember that the only way to make continental crust is at subduction zones. I hope you all recall that whole process of creating continental crust at subduction zones. If you do not remember that, go back and watch the plate tectonics lectures again, because it is an extremely important process that I've explained now several times. So the only thing we have is a single mineral from the Hadean. So we do think that, it's a kind of a mineral that's common in continental crust. So we think that there was probably continental crust, probably was plate tectonics at this time. So we have one zircon crystal from the Jack Hills, Australia, about 4.5 billion years, 4.4 billion years ago. Okay, so that's kind of just a summary slide. I've already kind of showed this one to you, but it's just a summary slide of everything we've learned so far. Just kind of a couple things I think are just interesting, kind of wrapping up here. When we first started out here on Earth, a day was only about 10 hours. That's because the Earth was rotating faster. Every day, the Earth's rotation slows down a little bit. So atomic clocks show that a modern day is about 1.7 milliseconds longer than a century ago. So, you know, every day, actually, the Earth slows down a little bit, and that's because of tidal effects, friction coming from the moon and its orbit around the Earth, okay? So if you extrapolate that rate of precession back, you'd see that a day was probably much shorter in the Hadean, probably only 10 hours. Another thing that's true is that the sun's luminosity back then was not as bright. So it was actually 70% dimmer back then. We got 70% less sunlight back then. So it was kind of, even though it was a very hot surface of the planet, the sun was not as powerful. So it was kind of perhaps, once the Earth started to cool, you know, the climate was probably cooler than it is today. Okay, way back then. Okay. Notice anything else that's missing in this picture? So you'll notice there's no trees, no animals, no life. So we're going to have to wait. There was no life during the Hadean that we know of. We're going to start life in the Archean, which will be the next lecture. So that's all for today. I know it's a long lecture. Hope you enjoyed it, and I will talk to you next time about the Archean.